imagine hiring a construction crew, right? And by default, they just take a huge wrecking ball to your house before checking if the new bricks have even arrived at the supply yard.
Yeah, just completely leveling the place.
Exactly. And that terrifying scenario, it isn't just a metaphor. I mean, it is literally exactly how Terraform operates out of the box.
It really is.
So today, we're diving into the official HashiCorp Terraform documentation and, the Associate 003 exam materials. We have to figure out how to tame that default behavior.
Right, getting the contractor under control.
Yeah. So our mission for this deep dive is mastering Terraform's lifecycle meta-arguments.
And just to put the stakes in perspective here, whether you are taking that certification exam or, you're a platform engineer managing a massive production environment, you really have to know how to override Terraform's deepest instincts.
Because if you don't...
Yeah, because if you don't, things go bad. Those lifecycle meta-arguments are like the specific life-saving instructions you hand to the execution engine. Without them, it could accidentally wipe out your entire network architecture during what you thought was just a routine update.
Right, a routine update turns into a complete outage. So we need to figure out how to get this automated contractor to behave.
Definitely.
And I guess the first step in taming the contractor is understanding why it wants to swing the wrecking ball in the first place.
Right, the logic behind the destruction.
Exactly. Because out of the box, Terraform follows a really strict destroy then create sequence. Like if you change a parameter that forces a resource replacement, it tears the old one down, waits for confirmation that it's gone, and only then builds the new one.
Which, to be fair, is a completely rational design choice for most foundational cloud infrastructure.
Wait, really? Rational?
Well, yeah, I mean, Terraform tracks resources by mapping your code to unique identifiers in the cloud provider's API, right?
Okay, sure.
So if you are provisioning a resource that requires an exclusive claim like, say, an AWS Elastic IP address or a globally unique S3 bucket name, you literally cannot have two of them occupying the same space at the same time.
Oh, because the cloud provider would just reject the API call.
Exactly. The API would throw an error. You have to clear the lot before you build the new structure.
Okay, I get that. But that rational logic completely falls apart the second we start talking about high availability systems.
Oh, absolutely.
Let's look at zero-downtime deployments. If you have a critical web application running on an EC2 instance and you need to update its Amazon machine image, the underlying OS blueprint Terraform's default behavior is going to destroy your running web server.
Leaving your users totally stranded.
Right. They're just staring at a 502 bad gateway error while it takes like 3 minutes to boot up the replacement. You are voluntarily inducing an outage.
And that is the exact problem the create before destroy meta argument was built to solve.
Okay, so how does it work?
Well, when you drop that block into your resource configuration and set it to true, you are explicitly flipping the sequence. Terraform will actually provision the new replacement instance first.
So it builds the new house first.
All right. It built it, and then it waits until the cloud provider confirms the new instance is healthy and running.
Okay.
And only then does it update its internal state references to point to the new infrastructure. And finally, it issues the destroy command for the old instance.
Wow. Okay, but this is where the execution mechanics get a little tricky for me.
How so?
Well, if I tell Terraform to build the new web server before tearing down the old one, I am creating a temporary overlap, right?
Which you are.
So I have two resources competing for the exact same configuration. If I hard-coded a specific name tag like, I don't know, production web server 01 in my Terraform code, the cloud provider's API is going to throw a validation error the second Terraform tries to build a replacement.
Exactly. You hit the nail on the head. The blueprint itself has to be designed to accommodate that overlap.
So I just can't use hard-coded names.
You really can't. Not if you want to use create before destroy. You have to use dynamic naming instead. In Terraform, that usually means using a name prefix argument combined with a random string generator. So Terraform will bring up the new instance with a slightly randomized name, say production web server NoxIZ.
And because the name is randomized, the API accepts it.
Exactly.
That makes total sense. Then I'm guessing to make the handoff actually seamless for the end user, you just sit those instances behind a load balancer.
Yep, that's the standard pattern.
So Terraform brings up the new randomized instance, registers it with the load balancer target group, waits for the health checks to pass so it's actively receiving user traffic, and then boom, it deregisters and destroys the old instance.
And the users never notice a single thing.
That's awesome.
It really is. You are basically orchestrating a blue-green deployment right at the infrastructure level. It's incredibly powerful. But create before destroy is fundamentally about managing things we want to replace.
Right.
We need to shift gears now and look at the resources that should never, under any circumstances, be touched by that wrecking ball.
Oh boy. We are talking about the catastrophic resume-generating mistakes here.
The worst of the worst.
Yeah, imagine a slightly sleep-deprived engineer who makes, like, a really minor configuration tweak to a security group, types Terraform apply, and accidentally triggers the replacement of the primary RDS instance.
Ouch.
Yeah, the managed database holding literally all the live customer data. Just gone.
That is the ultimate pit of the stomach moment for sure. And to stop that from happening, HashiCorp gives us prevent destroy.
Okay, the big red stop button.
Basically, yeah.
Yeah.
If flipping the order of operations is about managing the wrecking ball, prevent destroy is about putting a massive padlock on the demolition equipment.
I like that analogy.
When you set it to true inside a resource block, Terraform will outright refuse to execute any plan that involves destroying that specific resource.
So it just halts.
Completely. If the automated engine calculates a destroy operation, whether that's from a direct Terraform destroy command or an accidental replacement triggered by some minor change, it halts entirely and throws a fatal error.
But, and this is where Terraform's underlying logic gets a bit terrifying, and I know it's a major focus on the certification exam, that prevent destroy padlock is not an impenetrable shield, is it?
No, it is absolutely not.
Yeah, because it completely ignores a detarget flag. If an operator runs Terraform destroy detarget osdeepinstance.main, Terraform just bypasses the protection entirely.
Yep, it walks right past the padlock.
Why would it do that? It just assumes that if you are passing a specific target flag, you are like a break glass operator who understands the consequences and needs to force an override.
That's exactly the logic.
Yep.
The tool assumes user competence in the face of explicit manual commands.
Wow.
And the e-target flag isn't the only vulnerability either. Prevent destroy also does absolutely nothing to stop the Terraform state arm command,
which is the mechanism for untracking resources. Because we have to remember what Terraform actually is under the hood. It's not magic. It's an engine relying on a local or remote JSON file, the state file, to map your written code to the actual physical cloud provider IDs.
A giant complicated map.
Yeah. So running state arm doesn't actually send an API call to AWS to delete the database. It just deletes that JSON mapping.
Right.
You are literally giving Terraform selective amnesia.
That's a great way to put it, a selective amnesia.
The database is still perfectly intact in the cloud, but the contractor has just scrubbed it from their ledger.
And once it is removed from that state file, Terraform no longer manages it, which means Terraform no longer protects it.
So someone could just go in and delete it.
Exactly. A rogue script or another user could delete the database directly in the AWS console, and your automated pipelines wouldn't step in to prevent it at all.
That's wild.
The key takeaway here, especially for anyone managing production environments, is that prevent destroy is a safeguard against automated cascading failures during routine applies.
Right. It stops you from shooting yourself in the foot with a typo.
Yes. It is not an enterprise security policy against malicious actors or manual overrides.
Okay, so prevent destroy is great for static panic prevention, but there seems to be a fatal flaw in relying entirely on strict locks like that.
Which is?
Well, it assumes your infrastructure is entirely static. What happens when a resource is actually supposed to change on its own, completely outside of Terraform's control?
Ah, yes. That introduces the whole concept of configuration drift. And it's exactly where we bring in the ignored changes lifecycle argument.
Configuration drift. Okay.
See, Terraform's core philosophy is that the desired state defined in your code must perfectly match the actual state in the cloud.
They have to mirror each other.
Exactly. During an apply, Terraform does a three-way merge. It looks at your .tf code, it looks at the .tstate JSON file, and then it queries the live cloud API.
Okay.
If the live cloud API differs from your code, its default instinct is to aggressively revert the cloud back to match your code.
You know, it reminds me of the classic landlord-tenant problem.
How so?
Well, as a landlord, I care deeply if the tenant knocks down a structural wall, right? I want that reverted immediately.
Sure, yeah.
But if the tenant just rearranges their own living room furniture, I need to look the other way. If I walk in and force them to move the couch back to where it was on move-in day, I'm actively breaking their workflow.
That is a perfect analogy.
Yeah.
And that tenant behavior happens constantly in the cloud, specifically with auto-scaling groups.
Right.
Let's say your Terraform code defines an auto-scaling group with a desired capacity of 2 instances. The system is deployed, Everything is stable. It's all good.
Okay, 2 instances.
But then a massive traffic spike hits, like, say, a Black Friday event. The cloud provider's internal monitoring detects the huge load and dynamically ramps up the group to 10 instances to keep your application from crashing.
So the system is doing exactly what it's supposed to do. It's working flawlessly.
Yep.
But wait, if a platform engineer runs a routine Terraform apply at that exact moment, maybe just to update some billing tags on a completely unrelated S3 bucket Terraform is going to perform its state refresh.
And what will it see?
It will see 10 instances running in reality, but it will look at the .tf file, which explicitly says 2, and its instinct will be to immediately terminate 8 instances right in the middle of the traffic spike.
Exactly. It creates this active tug of war between your infrastructure as code pipeline and your dynamic runtime systems.
That's a disaster.
So to resolve this, you use the ignore changes block. You just provide a list of specific attributes, in this case desired capacity, that Terraform should explicitly ignore during its state comparison.
But hold on. By telling the system to ignore changes, aren't we kind of undermining the entire concept of infrastructure as code?
How do you mean?
Well, the whole industry moved to Terraform to guarantee a single source of truth, right? If we start ignoring attributes, we are deliberately losing visibility into what our infrastructure actually looks like.
I get why you'd say that, but it is a deliberate trade-off. You aren't losing the source of truth, you are redefining its scope.
Redefining the scope.
Yeah. By explicitly documenting ignore changes, desired capacity in your code, you are formally delegating responsibility.
Oh, I see.
Your code serves as the architectural blueprint that says, hey, Terraform handles the initial provisioning, the instance sizing, and the network attachments. But the runtime capacity, that is delegated to the dynamic scaler. It's intentional, securely documented drift.
Okay, that makes a lot of sense. So we've looked at protecting resources with locks and ignoring localized changes with drift, but infrastructure is a highly connected web.
Very connected.
Sometimes a change in one place absolutely mandates a reaction somewhere else. And I think this brings us to the newer mechanics of chain reactions, specifically the replace triggered FZB argument, which I know was introduced in Terraform 1.2.
Yes, and this is a really important one. Traditionally, Terraform only replaces a resource if its own internal configuration changes.
Right.
But modern architectures often decouple configurations from the actual compute resources that consume them.
What's a good example of that?
Think of a Docker container running on AWS ECS. The container pulls its environment variables from an AWS Systems Manager parameter store.
Okay.
If you update the database password in the parameter store, the ECS service itself hasn't technically changed its own configuration, so Terraform won't restart it. The container just keeps running with the old cached password.
Oh, man. Until the container crashes weeks later, restarts, pulls the new password, and you suddenly have a totally unexplained outage.
Exactly. A ticking time bomb.
So replace trigger by allows us to link their fates. We add the block to the ECS service resource and point it at the parameter store resource. When Terraform detects a change in the parameter, it forces a replacement of the container to ensure it picks up the new value immediately.
Spot on. It creates a forced dependency.
Yeah.
But the mechanics of how Terraform processes that dependency are what you really need to understand for the deep dive here.
Okay, let's get into the weeds.
Terraform operates by constructing a directed acyclic graph, or a DAG.
DAG.
Right. It is a literal map of every single resource, represented as nodes, and the dependencies between them, represented as edges.
And this is where my head starts to spin a little bit.
It's complex, for sure.
Because if resource A triggers a replacement in resource B through replace trigger by, but resource B also has a standard dependent relationship with resource C, meaning B cannot be built until C is finished, how does the execution engine map this all out?
Right. Without breaking.
Yeah, how does it not just freeze in an infinite loop or tear down the wrong thing?
Well, the key is in the name, because the graph is acyclic, meaning there are mathematically no loops allowed. When Terraform reads your configuration, it topologically sorts the graph before it takes any action whatsoever.
Okay, topological sorting. So in plain English, that means it is laying out all the dominoes in a single unbranching line.
I love that visual, yes.
It calculates the entire sequence of events based on both the replace trigger by B triggers and the dependent rules, and it ensures no domino falls until the one strictly before it is fully settled.
That is the perfect way to visualize it. Replace triggered by adds a new dynamic edge to the graph, telling Terraform what must be replaced, while the topological sort determines the strict when.
Wow.
Terraform evaluates that entire graph during the plan phase. It maps out the cascading replacements, ensures all dependencies are satisfied in the correct order, and presents the full chain reaction to you before a single API call is even made to the cloud.
Which is just an incredibly elegant piece of engineering when you think about it.
It really is.
But, all of these mechanisms, flipping the wrecking ball with create before destroy, adding those padlocks with prevent destroy, delegating responsibility with ignore changes, and orchestrating the dominoes, they are fairly straightforward when you are managing individual resources in a flat file.
True. But real enterprise environments don't work like that.
No, they don't. We use modules. We package resources into reusable, standardized black boxes.
And that introduces the module trap.
The module trap. Let's talk about it.
It is notoriously difficult to navigate in practice and heavily featured in the Associate 003 exam. When you are writing a root configuration and you call a module written by someone else, say a central platform team at your company, you do not have direct access to the resources inside it.
Right.
The hard rule is that a module caller cannot override lifecycle rules that have been hard-coded inside the module itself.
Wait, so if a platform team writes a standardized database module and they just hard-code prevent destroy true on the database resource inside that module, I can't just pass a variable into the module block for my root code to turn it off.
Nope, you can't.
I can't write lifecycle prevent destroy false at the module level. The hood is basically welded shut by the module author.
The hood is welded shut. The execution engine evaluates lifecycle blocks in the context of the child directory, where the resource is actually defined, not the root directory where the module is called. Terraform simply does not support dynamic variables or external overrides for lifecycle arguments.
Wow, this limitation is exactly what trips people up in the real world, isn't it? All the time.
And on the exam, it requires you to intimately understand where these rules need to be applied. Let's weave this into the kinds of scenarios engineers actually face.
Let's do it.
We get a panic ticket because an automated pipeline accidentally dropped an RDS instance. The instinct is to just slap prevent destroy on everything.
Sure, a knee-jerk reaction. But if they apply prevent destroy to the module call in the root file, Terraform will just throw a syntax error. The padlock has to be placed on the OSB instance resource deep inside the module's actual source code.
Ah, okay. And the same goes for the autoscaling group fighting the dynamic scaler, right? We see the instances terminating during a deployment. We know we need ignore changes on the desired capacity.
Right.
But if the ASG is buried inside a vendor-provided module, we can't just patch it from the outside. We are stuck fighting the module's predefined logic.
Exactly. And that exact friction leads to the most common exam trap you'll see.
Okay, what is it? The test will present a scenario. A critical resource inside a module has prevent destroy. True. The question will assert that because the caller cannot override the lifecycle rule, the resource can never be deleted under any circumstances.
Which, sounds completely logical based on everything we've just discussed. If the hood is welded shut and dynamic variables aren't allowed, it implies a permanent lock.
Right.
So how do you actually bypass it? Because you can't just run a force command to ignore a lifecycle block. Right?
No, you can't. But that assertion is unequivocally false because it ignores the fundamental nature of infrastructure as code.
Which is?
Terraform configurations are just text files.
Oh, wow.
Yeah. Prevent destroy is just a configuration state. It's not a physical property burned into the cloud hardware. If you are dealing with a local module on your machine, the bypass is literally just manual text editing.
You just delete it.
You open the modules.tf file, physically delete the prevent destroy block, save the file, and run Terraform apply.
Okay, so you are updating the state file's understanding of the rules. By removing the block and applying, Terraform updates its internal DAG. The node representing the database no longer has the protection flag.
Exactly. And once that apply finishes, you can immediately run Terraform destroy, and it will tear it down without a second thought.
So it requires a two-step process. Remove the rule, synchronize the state, then execute the destruction.
Yes. But if you are consuming a remote module from, say, a private registry or GitHub, you cannot edit the file directly on your machine.
Right, because it's pulling from a remote source. So what do?
You have to actually fork the module repository, remove the lifecycle block in your fork, update your root code to point to your new modified source, run apply to clear the state lock, and then destroy it.
Wow. You have to systematically unweld the hood before you can dismantle the engine.
That's exactly it.
It proves that Terraform only enforces the rules that are currently present in the merged graph of the code and the state file.
Which brings us to a really fascinating realization about the tool itself.
Yeah.
We have spent this whole deep dive analyzing the strict, unyielding logic of Terraform's execution engine, right?
Absolutely.
We've seen how create before destroy manipulates API sequencing, how ignore changes forces the state file to look the other way, and how replace trigger B dynamically alters the topological, sort of the dependency graph.
Yeah, we've mapped out the exact mechanisms you need to safely pilot this massive automated construction crew. You have the tools to dictate exactly how and when the wrecking ball swings.
But when we look closely at the ultimate guardrail prevent destroy, and we realize that it ignores targeted commands, it is entirely blind to state file manipulation, and it can be completely dismantled by simply deleting a line of text and refreshing the state.
Right.
It leaves us with a critical question about security architecture for you to think about.
Okay, lay it on us.
If the ultimate lock can be bypassed that easily by anyone with commit access to the repository, is prevent destroy actually a robust security feature? Or is it really just an elaborate engineered psychological speed bump, designed solely to force an operator to take a deep breath and think twice before hitting enter?